The Chapter 5 pretest, though, is exactly to get you prepared for today's class. So we will be going over the concepts that you've seen in the Chapter 5 pretest. And it's a good thing that you asked that, because this is a good example of one of the pretests where I don't expect many of you to be able to get 100% on the pretest, necessarily learning this on your own. This is where the kind of level of difficulty in learning the material on your own increases. However, doing the pretest, make no mistake about it, doing the pretest sets up your mind to get ready for today. Doing a pretest has been shown to increase your learning outcomes at a later time, even on the ones that you get wrong. So there is a lot of research that shows it's not just on the ones that you work at and you get correct that you benefit from, but even if you work a question and you just can't get it and you still can't get it, you still show benefits. People who do pretests and get the questions wrong end up learning more by the end than people who do not do a pretest. So this is where the pretest, I understand, will get a little bit more ramped up in difficulty, but do not get frustrated. Give the pretest a good try and know that you have the mastery points that you can fall back on in order that the pretest grade doesn't affect your final grade. So it's all part of the system of making sure that you get exposed to it, making sure that you struggle with it in order to benefit your learning experience. But definitely this is one of the ones where it's a good day to be here, because hypothesis testing is a long chain of steps, and to keep all of that in your mind all at once is a little bit more challenging than what we've been doing up to now. If you want to, however, if we need to go over the Chapter 4 stuff, next time that we have practice time, definitely we can do that. Come by my office hour, we'll be able to do that. But just today's class, actually, I don't even know if we're going to get to the end of today's class because it is just so filled with, in this case, 3 examples to kind of introduce hypothesis testing to you so you can see it now in its full form 3 times through. All right, so once again, we are now doing hypothesis testing. This is the cool stuff that was promised to you in stats. This is probably the stuff that you thought you were going to be doing in statistics. Taking a look at real psychological data, applying stats to real psychological situations, and seeing how real-world problems are solved using the statistics of hypothesis testing. So this is the stuff that, these are the techniques now that professional psychologists, faculty here, will use in their own research. It's also a lot of the techniques that many of you will use when you're doing your advanced lab. So some of the tests that we're going over now, we're doing them because they are some of the most common tests used in psychology, which means that when you do your advanced lab and you need to analyze your data, these are the tests that you will probably need to use. So today what we're going to be doing is we're going to be taking a look once more at a recap of the core logic of hypothesis testing, just kind of get that idea in your mind, get that squared away, even if it's just through repetition. We're going to take a look at another perspective to hypothesis testing so you have a different view on it that might make more sense to you. It's the same idea, but just from a different perspective. And then we're going to go through the process. We're going to take a look at the Self-Esteem and physical education program example. We're going to do that twice. And then we're going to continue our look at hypothesis testing by taking a look at the Harlow and Zimmermann infant attachment study that you probably heard of in your general psychology course. All right, so once again, the core logic of hypothesis testing. What the goal is, what we're trying to do, where psychology gets its power, is we are taking a look and using a systematic procedure to go from what we can measure about a sample and correctly infer what that tells us about the entire population. So it's always about starting with a sample, sometimes even as low as 1 individual, and using this process to predict what is true of the population, to make sure that psychology isn't just for the few, the sample, but it's for the many, it's for the population. And as we saw last time, The question that we want to answer is that if we have a population and we apply a treatment that we came up with to the entire population, will that population change? That's the question we're trying to answer. And we can't do that either ethically or just, for example, financially, time-wise, we can't do that. So what we do as psychologists is we take a sample from that untreated population and we treat that sample. We do an experiment on that sample, and then we measure what happens to the sample. And the question we're asking is, has this sample changed enough to indicate that it now belongs to the new treated population? It now belongs, it no longer belongs to the old population. Our treatment is effective and has changed this sample enough to indicate that it belongs to this new population. Now, one thing that's going to seem a little bit strange today when we take a look at the first examples is that just to simplify the teaching procedure, the first example that we're going to look at assumes that you did not measure your sample before you treated it. So that's a little bit weird, so just bear that in mind. It's just there for educational purposes. We're going to get later on to the more complex situation where you measure the sample first, you measure the sample again later. But really what we're asking is, does this treated sample, this sample after treatment, does it still belong to the original population, right? If it does, that means that your treatment does nothing. But if your sample has been transformed and it no longer belongs to that old population, it means that your treatment has done something. It's changed the sample. It has changed the population. So another way to look at this is to realize that if you have this known population, right? So we're starting with a known population. If you have a known population and you have this sample from the known population, there's the mean of your population. There's the mean of your sample. And there's going to be some difference between the two, right? We have the mean of the known population. We have the measured mean of the sample. And there's going to be some difference between the two. And what we're answering here is, where does that difference come from? Why does that difference exist? So there's two possibilities. One possibility is that your sample still belongs to the pre-treated, untreated population. And what that means is that your treatment does nothing. If you've treated your sample and it still belongs to the old population, if you've taken a sample of depressed individuals, given them your treatment, and they still belong to the depressed population, then your treatment does nothing, and we accept the null hypothesis. We accept the idea that the treatment does nothing. On the other hand, if because of that difference, we realize that your sample now no longer belongs to the old population, but instead belongs to the new population, well, that means that your treatment has done something. It has changed these people. They used to be depressed, but now they belong to the non-depressed population. That means your treatment does something, and that's when we reject the null hypothesis and we accept the research hypothesis. So that at the core of it is what we're trying to determine. This new treated sample, where does it belong? Does it belong to the old population, or does it belong to the new population? Now, you'll notice that we don't know anything about this new population, right? We don't know what the mean of this new population is. So we can't compare this sample to see if it belongs to the new population. All we can do is we can compare this sample to see if it belongs to the old population. And that's the choice that we're making. Does it belong to the old population? If so, treatment does nothing. Or does it not belong to the population anymore? If so, your treatment does something. So again, we have the mean of the untreated population, the known population. We have the mean of our sample after it's been treated. And there's going to be some difference between those two. And the question is, where did this difference come from? Now, it could have come from the treatment. That's one possibility for why we have this difference between our sample mean and our population mean.
But the other place that it could have come from, other than the treatment, is just from the weirdness of our sample. So if you recall before, when we looked at samples being used to estimate population parameters, that sample that we took from our population might have been this sample, right? That might have been the sample that we started with from our population. And when we treated it, it became more extreme. The mean of it actually changed. So that's one possibility. We had a sample that was representative of the population, and our treatment is the reason for the new mean. The treatment is the reason our sample is different. On the other hand, it could be that we had an extreme sample. And it could possibly be that the reason we have a difference between the population mean and our sample mean is because our treatment didn't do anything, but we started with an extreme sample. We started with a sample that just by chance came from an extreme end of the population, and that's why we found the difference that we found. So there's always those two possibilities. One, that our treatment actually worked, and it changed a sample into this new sample. The other possibility is that we just started with a really weird sample. We just started with an extreme sample, and that's the reason for the difference that we found. So the challenge here is that we never know where our sample actually came from. So we don't know, again, if that difference is due to the treatment or is the difference due to an extreme sample, right? Is that why we ended up with this difference? However, we do know from what we've seen before, from that central limit theorem, we do know that some samples are more common. Some samples are more rare. Extreme samples, for example, are more rare. They're less probable to occur. So what the core of hypothesis testing really is really saying, all right, let's say that our treatment does nothing and this sample came from the population, right? Let's say that it came from this known population. What is the probability that this sample could have come from the known population? Because there is a probability, right? We could have just chosen 5 people that are just from the extreme side of the population. That is a possibility. If it's extreme, our treatment did nothing. So what we want to do is we want to figure out, well, what are the odds of getting a sample from the population that is this extreme? If that probability is highly likely, if we say, well, based on this difference, getting a sample that would have this much of a difference, that's pretty likely, right? That's pretty likely to have occurred. If that's the conclusion, that this difference here can occur with a highly likely sample, then we say that the treatment does nothing and we accept the null hypothesis. We say that this sample probably still belongs to that untreated population. If, on the other hand, we find that it is highly unlikely that we would ever end up with a sample this weird from this population, if it requires many extreme examples, if it requires Bill Gates and Neil deGrasse Tyson and Marilyn Savant, if it requires all of those individuals, then that sample is highly unlikely. So the treatment in that case does something, and we reject the null hypothesis. So another way to think about this is that you can assign a probability to how extreme your sample is. So if we take a look at this sample here, and we give the probability of getting that sample, right? What's the probability of getting a sample this extreme or more extreme? And let's say that the probability of that is 50%. That means that the difference that we found could be due 50% to the sample that we got, or there's a 50% chance, sorry, I'll rephrase it. There's a 50% chance that it's due to the sample, or there's a 50% chance that it's due to the treatment, right? Because it's going to be one or the other. Either your treatment does something and that's the reason you have the difference, Well, your sample does something, and that's the reason you have the difference. So if the difference might have been caused by the sample with a 50% chance, that means that your treatment has a 50% chance to have caused that difference. On the other hand, if we take a look at this sample and we say there's only a 4% chance of getting a sample this weird from that population, well, that means that there's a 96% chance that the difference we're seeing is due to the treatment. And this is the situation where you would say, you know what? Sure, there's a 4% chance that maybe it's an extreme sample, but I'm 96% certain that my treatment did something. That's the case where you would conclude that your treatment is effective. So we're talking about whether the sample is likely to have come from the known population, the untreated population. Was it unlikely to come from the population? And now the last thing we got to do is we got to nail down how likely is likely. We got to be very explicit about that amount. And that amount is going to be your line in the sand. And that amount is the alpha level. And that alpha level is usually, though not always, set at 5%. Right? So you usually see an alpha level of 0.05. What that means is that we're setting that likelihood at 5%. And there's entire articles written on why 5% kind of makes psychological sense. We won't go into that today, but that's where your line in the sand is. So when somebody says, well, how likely is likely? The answer in this case is your alpha level. It's your 5%. So if your sample is greater than the alpha level, right? If the probability of getting a sample that extreme is 50% and your alpha level is 5%, you accept the null hypothesis. You say that your treatment, you say that your treatment did nothing. If on the other hand your alpha level is less than, if on the other hand your sample percentage is less than your alpha level, if the chances of getting a sample that extreme is 4%, that is less than our alpha level of 5%, in that case we reject the null hypothesis and we say that our treatment is effective. We say that our treatment did something. So that's the probability that the sample came from the unknown population. Again, if the probability is greater than your alpha level, your line in the sand, then your treatment does nothing. If, on the other hand, your probability is less than your alpha level, in this situation here, then you conclude that your treatment actually did something, and you would reject the null hypothesis, the hypothesis that your treatment does nothing. So that in its essence is what hypothesis testing is all about. What we're trying to figure out is if our treatment did nothing, if our treatment was effective, what are the odds that we would get the difference that we found? And if the odds are below our alpha level, if it's a really, really unlikely chance that we would get a difference that big just by a weird sample, then we say, all right, high probability that our treatment does something. We're going to conclude our treatment is actually doing something. If, on the other hand, that difference is highly likely to have occurred just because you chose a weird sample, then you would say that your treatment does nothing, and you would say it's probably just an extreme sample. So that is what we're looking for. That's what the entire system is designed to decide. All right, so let's take a look at an example of this. When we last left, we introduced the 5-step procedure. So that 5-step procedure is just a formalization of this logic. It's just a step-by-step recipe for making this final decision. So we've already seen the hypothesis testing procedure for step 1. Is there a difference between the treated population and the known or untreated population? So we're going to go through this a little bit quickly right now so we can put it into practice. And we've seen this one before. Is there a difference between the treated population and the known or untreated population? Notice, first off, your null hypothesis and your research hypothesis is always about the populations. You are never asking about the sample. You're using the sample to get to populations. So your research hypothesis is that the treatment does have an effect and that the mean of your treated population will be different from, not equal to, the mean of your untreated population. The null hypothesis is that the treatment has no effect. And what that means is that the mean of your treated population is exactly the same as the mean of your untreated population because your treatment has done nothing. All right, step 2. This is new stuff. Determine the characteristics of the comparison distribution. So this comparison distribution is the distribution that is going to represent your unknown population. It's going to represent the population. If your null hypothesis is true, it's going to stand in for the population where your treatment does nothing. And this is where you're going to compare your sample mean to this comparison distribution. And I'm highly emphasizing the fact that you are comparing your sample mean to a distribution that represents the population distribution, because it is not the same as the population distribution. It is the distribution of sample means. So you're comparing a sample mean to a distribution. It is unfair, if your sample is larger than 1, to compare a group of people to a distribution of individuals. Your population is a distribution of individuals. Your sample mean is a measurement based on a group. And again, it is unfair to compare the performance of a group to the performance of an individual. It's like playing a basketball game that's 5-on-1, right? It's not a fair comparison. So instead of comparing our sample mean to a distribution of individuals, we're going to compare our sample mean to a distribution of sample means. Makes way more sense. So we're going to compare our sample mean not to the original population distribution, but to that distribution of sample means. And that's why we were spending so much time on the normal curve, because as we saw before, that distribution of sample means is a normal distribution. So be very careful about that. The book starts you off with a hypothesis testing procedure based on single scores, based on individuals. And that's why in Chapter 5, it's fine to compare it to the population distribution, because the distribution of sample means and the population distribution are exactly the same when your sample size is 1. I don't like that. We're going to start off with samples right away, so that when we switch gears in Chapter 6, it's not going to be abrupt. It'll be the way that you learned it the whole time. So that's why we're starting off with samples, and we're going to compare our sample mean not to a population distribution, not a distribution of individuals. We're going to compare our sample mean to a distribution of sample means. So that's step 2, determine the characteristics of that distribution. Step 3, we're going to set a cutoff sample score or critical value. This is the line in the sand where you say that sample mean is different enough. So we're going to find a line in the sand on our comparison distribution where if the sample mean crosses that line, we're going to say the sample mean is different enough, the treatment is effective. If the sample mean does not cross that line, we're going to say the sample mean is not different enough. So this is just a hard line, I call it the line in the sand, where you're going to compare the results of your study, your sample mean, to that line. Step 4, we determine our sample score in the comparison distribution. So step 3, we draw the lines, we determine where the lines are. Step 4, we determine where our sample mean is. So we figure out, has it crossed the line or has it not crossed the line? And then finally, step 5, we decide whether to accept or reject the null hypothesis. So we compare our sample's z-score, and we're doing z-scores because this is all going to go through the z distribution. We compare our sample's score to our cutoff score, and if the sample z-score is beyond the cutoff z-score, that is, it's crossed the line, our sample has crossed that line in the sand, we accept the research hypothesis, and we reject the null hypothesis. If, on the other hand, the sample score is within the cutoff z-score, it has not crossed that line, we accept the null hypothesis. We say that our treatment has done nothing, it's just a slightly weird sample, and we reject the the research hypothesis. All right, so that is the hypothesis testing procedure. And I know that was probably not making a lot of sense right now. So what we're going to do is we're going to put it into practice, and hopefully when we tie it to an actual example, it'll start sinking in and you can build your kind of cognitive structure to understand the entire process. Mm-hmm.
Now, when you say cutoff, is that the 5% or the 0.5%?
Yes.
Oh.
Yep. The cutoff score is determined by the 5%.
Okay.
And we'll see what we mean by that when we build this up piece by piece. All right, so back to the school. So if you remember the example from last time, you're an educational psychologist, you graduated from IUSB, you get a call from an elementary school, and they're worried about their children. They're not performing as high as they would like, and they suspect maybe it has to do with their self-esteem. They were hoping that you could find a program to increase their self-esteem. So you go to the school and you realize that their physical education program is nothing but push-ups and drills, and you devise a new treatment, a new program that is based around gameplay so that the students, still get their physical education, but not in the sort of competitive drill paradigm, but with this new games play initiative. And what you want to know is, if their self-esteem improves, does that mean that your treatment will work for the population of individuals, will work for the population of students? Or if their self-esteem is higher than the national average, was it just that you got a weirdly high self-esteem group of students? So that's what we're going to compare. We're comparing these group of students to the national average to see whether or not your treatment has made a difference. So for this, what I've done is I have set up a Excel sheet. So this is the Excel sheet right here. So if you haven't already, you might want to open this up in Canvas. And then what this is basically the 5-step breakdown right here. But this is what it's going to look like when it gets tested in the next exam. So this is what the hypothesis testing is going to look like. So to kind of practice just what information you'll be asked for, you can follow along in that Excel sheet. All right, so here's the situation. So a researcher is evaluating the effectiveness of the physical education program, the games program, for elementary school students. The program is designed to reduce competition and increase individual self-esteem. A sample of 16 children is selected, and the children are placed in the new program. As soon as I read sample of 16 children, I know we're dealing with a normal distribution. I know that this has now opened up psychology so that we can actually analyze this results. So a sample of 16 children is selected, and the children are placed in the new program. After 3 months, each child is given a standardized self-esteem test. Now, you might be sitting there looking at this example saying, well, wouldn't it make sense to test them before on their self-esteem, before the program, and then test them after the program? And you're absolutely right. It does make sense. It makes a whole lot of sense. Slightly more complicated hypothesis testing procedure, which is why we're saving that till later. So let's just assume that the research assistant forgot to measure their self-esteem before the program. So now we're measuring their self-esteem after the program. So after 3 months, each child is given a standardized self-esteem test. For the general population of elementary school children, the scores on the self-esteem test form a normal distribution with a mean of 40 and a standard deviation of 8. So this is one of those rare occurrences where we're dealing with a standardized test where we know the population mean, it's 40, and we know the population standard deviation, it's 8. So the question now is, if the sample mean for these students is 43.5, is this enough to demonstrate a significant effect? Significant effect means that your treatment is effective, your treatment will work for the population. That's just a shorthand way. Significant effect means that your treatment is effective. So we're going to assume a two-tailed test with an alpha of 0.05. So what that means, well, we'll get to what a two-tailed test means a little bit later. We're just building up the foundations right now. All right, when you're doing a hypothesis test, every hypothesis test we do from here on out is going to follow this 5-step procedure. So it's going to be tweaked a little bit from test to test, but the basics of it does not change. So let's start with step number 1, restating the question as a research hypothesis and a null hypothesis about the population. What we want to know is there a difference between the game program student population and the general student or untreated population in terms of self-esteem? So on self-esteem scores, is there a difference between the students that did the games program and your typical average student from the population? That's the question we want to know. The way that it's phrased right now, we can't apply statistics to it. So the first step is we got to rephrase it so that we can open up this statistical procedure. And getting a null hypothesis and getting a research hypothesis is the rephrasing. So the research hypothesis in this case is that the games do have an effect. Your games do something. And we write that out as the mean of the games population does not equal the mean of the general population. So if you're following along in the Excel sheet, this is when you would go to that yellow answer cell that has less than or equal to, not equal to, greater than or equal to. And what you would want to do is you would want to erase I'll just show you this the one time. In an exam, you would want to erase hold on a second, where'd my thing go? You would want to, there we are. You would want to go into there and basically erase that to indicate the research hypothesis. All right, so that's how the Excel sheet would work. Same thing for the null hypothesis. However, we're not quite at the null hypothesis quite yet. So that's the research hypothesis, that your treatment did something, the games do have an effect, and we will be able to conclude this if the mean of the games population, the mean self-esteem for the games population, does not equal the mean self-esteem of the general population. This means that our treatment has changed this population. Our treatment has an effect. The null hypothesis, on the other hand, is that the treatment does nothing. The treatment has no effect. And we write this as saying the population of students that are using the games program have the same, equal, mean self-esteem as the population of general students. So there's no change in self-esteem. No change in self-esteem means no effect. So now we got the research hypothesis, we got the null hypothesis. Now we can continue on with our hypothesis testing. All right, so step 2, determine the characteristics of the comparison distribution. We're going to learn how to do this in chapter 6. For right now, what I want you to realize is that your comparison distribution is not your population distribution. It's only your population distribution when you have a sample size of 1, like this example right here. All right? Only when you have a sample size of 1, i.e. only in chapter 5. As long as you have a sample size that is larger than 1, 2, 3, 4, 5, for example here, 16, your comparison distribution is not your population distribution. And I'm going to drive this home because this is the most common mistake where students get into the habit of comparing their sample to the population distribution because they're starting off in chapter 5 with a sample of 1 and it messes them up in chapter 6 and beyond. So I'm going to drive this home a few times. You're comparing your sample mean to a distribution of sample means. So we're going to learn how to do this in the next chapter. For right now, it's got to be given to you. And your distribution of sample means has a mean of 40, and it has a standard deviation of 2. So that is our comparison distribution. So we have, let me get the black marker out here. We have a distribution of sample means here that has a mean of 40, and it's got a standard deviation of 2. Not the same as the population distribution. That is our distribution of sample means. All right, step 3, set a cutoff sample score or critical value. This is the target against which you're going to compare your sample mean to. And we're going to see how to do this soon. I don't want to overwhelm you with all the details. So we're going to give it to you right now. And for an alpha of 0.05, that's your cutoff scores. Where do we get those cutoff scores? Well, these cutoff scores, you can see the little z-score right there. Those are cutoff scores on the normal distribution, the unit normal distribution. And the reason for that is plain and simple. We don't have this distribution in our textbook. There is no distribution in our appendix that has a mean of 40 and a standard deviation of 2. You can flip through the appendices, you're not going to find it. So what we need to do in order to do this hypothesis test is we need to take our distribution of sample means and we need to transform it into a z-score distribution that has a mean of 0 and a standard deviation of 1. All right, and this transformation of scores into z-scores is what we've been doing since chapter 2. We've been taking raw scores and transforming them into z-scores. So we're building on those skills we've been developing. And if we, using an alpha level, put, and we'll find out how to do this, if we use the alpha level to determine our lines in the sand on this unit normal distribution, z normal distribution here, those lines in the sand are going to be a positive 1.96 and it's going to be a negative 1.96. So what this really means is that if our sample mean crosses into this tail over here, or if our sample mean crosses into this tail over here, it has gone too far. It has become too extreme for us to still think that it belongs to the untreated population. It's just too wild, too extreme. If it stays in here, that means that it's likely to have come from our untreated population. So the last thing we got to figure out is whether our sample crossed over into either one of these extreme sections here. If it goes into an extreme section, that means that it's either a really unlikely extreme sample or our treatment is effective. And this line in the sand is our way of saying this is how effective it needs to be before we're willing to make that conclusion. All right, so we have our lines in the sand. We have our comparison distribution. Step 4 now, we got to determine our sample score on the comparison distribution. So for this, we have to figure out our sample's z-score. This is why we've been doing z-scores so much in preparation for right now. So if we take a look at a question, we know that our sample mean is 43.5. That's what we measured. We gave everybody the test. Test came back, we tallied it all up, 43.5. 43.5 puts our mean somewhere there, right? So in our distribution of sample means, the sample mean that we found is somewhere there, right? Here's 40, this is 43.5. But has this crossed the line or has it not crossed the line? Well, we can't tell because we have no lines here. We got lines over here. So the last thing we need to do is we need to transform our sample score into some z-score. We need to transform this into a z-score so we can figure out where it is on this distribution over here. And the way that we do that is we have our raw score, we have our distribution mean, we have our distribution standard deviation. Make sure that you're using the proper distribution. It's the comparison distribution, comparing a mean to a distribution of means. So we have all that information. We have our formula for a z-score that we've been using since chapter 2. We plug it all in, and we get a z-score of 1.75. So we have transformed this 43.5 score on this self-esteem questionnaire to a z-score of 1.75, and that puts it right about there. That's where our sample mean has ended up, right? That's 0 right down the center, This line is at plus 1.96. 1.75 comes in right about there. Importantly, it did not cross the line. So our sample did not cross into that extreme zone, into that, it didn't cross that line. So we've calculated out where our sample is on our Z distribution, and now we just have to make a decision. Is our treatment effective or is it not effective? So spoiler alert, we didn't cross the line, our treatment's not effective. But I highly recommend, until that makes complete sense to you, refer to these two slides, because you'll be amazed at how easy it is to get these conclusions jumbled up in your head. And I'm always very frustrated when I see students do all of this correctly, end up with their sample in the right place, and then make the wrong decision at the end. So until this is rock solid, refer to these two slides. If the sample Z-score is beyond the cutoff Z-score, we accept the research hypothesis and we reject the null hypothesis. So if this sample Z-score went beyond the cutoff, no, it did not. So no, we will not do that. If the sample Z-score is within the cutoff Z-scores, if it stays within the body here, yes it did. That's exactly where it is. So what do? We accept the null hypothesis and we reject the research hypothesis. So once again, we figured out our sample Z-score, we figured out our cutoff Z-scores, and based on that decision, those two decision slides, we decide to accept the null hypothesis. That means that our treatment does nothing, and the fact that we had this slightly higher self-esteem score is just because we just happened to get an extreme sample, right? It was highly probable that we got that extreme sample. So our conclusion is that the GAMES program does not change the self-esteem of students compared to the general student population. All right, so that is the hypothesis from front to back. And if this was the result, as a psychologist, you would take a look at your GAMES program and you would say, oh well, it didn't work. Time to go back to the drawing board, time to go back to the theories, and try to come up with a new program that would actually serve these students. All right, any questions on that general procedure? Okay, so before we continue on, just to make sure that everybody's on this kind of same page here, there's my mouse. So for this one here, if we were filling this out with our Excel sheet, that is your null hypothesis right there. That is your research hypothesis. This Z critical is your lines in the sand. So we got 1.96 for your line in the sand. That Z sample is your sample Z score. In this case, it was 1.75. And then when you make your decision, all you do is decide whether you're going to accept or reject the null hypothesis. So in this case, we accept the null hypothesis, and we would reject the research hypothesis, and that is that would be graded as correct in, for example, an exam situation. All right, so typically you would just erase whatever it is that you don't need, but in this case I'm working backwards, so I just wrote it out. Yep?
Step 3, how did you calculate that Z-score? Which meaning did you?
Oh, the critical Z-score?
Yeah.
That one we're going to show next time. So right now I just want to get the kind of procedure going rather than like, let's do everything all at once. So we will definitely show you how to get that score. But for right now, let's work on step 1, step 4, and then step 5. So you will eventually get to the point where you can do this completely by yourself. We'll eventually get to the point where we do step 3 will be the next one we introduce. And then after that, step 2 will be the final one we introduce, and then you'll have all 5 steps. Mm-hmm.
And why did you use the standard deviation of 2 instead of 8?
That's step 2, and we'll get to that. So I'm glad you're asking those questions because that kind of shows that things are making sense to you because you're noticing things that don't make sense right now. We will get to step 2, we will get to step 3 as part of the complete package, but right now I just want to make sure we're solid on steps 1, 4, and 5, and just on the general makeup of everything. All right, so let's do this one more time. So let's say that we finish this experiment. We've just analyzed our experiment. Oh no, our sample did not cross into the extreme area. So we reject the null hypothesis and we say to ourselves, well, I guess my games program didn't work. Back to the drawing board, back to the theories. You want to help these kids increase their self-esteem. You want to help the population increase the self-esteem of their students. So let's find another treatment program. Let's say that at that moment we get a knock on our door and our research assistant comes running in and the research assistant says, oh my goodness, I'm so sorry, but I scored the tests incorrectly, right? I forgot to include one item. So she rescored the tests and lo and behold, instead of a mean of 43.5, we have a mean of 44.5. All right, so the actual sample mean, not 43.5, the actual sample mean is 44.5. And this is a great example of why we need a systematic procedure. Because if I was to tell you that, oh, our mean has now changed from 43.5 to 44.5, your human mind is probably telling you, big deal, 1 point difference. It's not going to mean anything. We're going to see if it means anything. So, once again, mistakes were made. And our original 43.5 mean for our sample was incorrect. It was actually 44.5. Let's see what this changes in terms of our hypothesis test. All right, so we are still going to do the same 5 steps. And luckily for us, most of these steps are going to stay exactly the same because it's the same situation. So for the research question, we're still interested in the same question. We're still interested in, do our game students have different self-esteems? Have our treatment made a difference? Does the game student population, is there a difference between them and the general student population? Because of that, our research hypothesis stays exactly the same. Is that the mean self-esteem of the games population does not equal the mean self-esteem of the general population. And our null hypothesis stays exactly the same. So the treatment has no effect. The mean of the games population is the same self-esteem as the mean of the general population. So very nicely, step 1 has not changed. Very nicely, step 2 has not changed because we're dealing with the same population. So we're dealing with the same distribution of sample means. So our comparison distribution has not changed. It still has, and we'll still see how to do this next chapter, it still has a mean of 40 and a standard deviation of 2. So far so good, nothing has changed. Step 3 has not changed. Our cutoff scores, this is a little bit of a spoiler alert, they're based on your alpha level. And we're going to see how to do this soon, but our alpha level hasn't changed, so our cutoff scores haven't changed. It's still plus 1.96, a z-score of plus 1.96, and a z-score of minus 1.96. So all that's the same so far. Where does the change occur? Well, the first change is in step 4, determining your sample score on this comparison distribution, determining the z-score for your sample. That's changed because our sample has changed. So our sample mean is now 44.5. It is not 43.5. But notice, on this comparison distribution, I don't know where that 44.5 is. I have no idea because there's no lines on this thing. There's no lines in the sand. We've converted this into the z distribution so we can put those lines on the sand, those cutoff scores. So now we have to figure out, well, where's this 44.5 on this distribution here? We got to figure out what is the z-score for that 44.5. So we have 44.5 is our sample mean. That's our raw score. A mean of 40 and a standard deviation of 2. That's the mean and standard deviation of our distribution. Using that formula for z-scores, we plug it all in. And now we find out that we get a z-score of 2.25. So this 44.5 is a z-score of 2.25. So what that means is that if this is 0 on our normal distribution, and this is 1.96, well, 2.25 has now crossed into the extreme zone. It has now crossed into the tail. It has now crossed that line in the sand. So we are either dealing with a really, really unlikely sample, or we're dealing with an effective treatment. And it's crossed that line, so that means that our treatment is effective. So when we go to step 5, this time, if the sample z-score is beyond the cutoff z-score, yes it is, now we're going to accept the research hypothesis and reject the null hypothesis. We're going to accept the idea that our treatment is effective. We're going to reject the idea that our treatment does nothing. If, on the other hand, it was back in the other situation, it was somewhere here inside the body, and it did not cross into one of these extreme zones, well, then we would have had the exact same conclusion we did last time. We would have accepted the null hypothesis and rejected the research hypothesis. So we have a score for our mean that goes beyond the cutoff scores, a score for our mean that puts it into the extreme zone. So we reject the null hypothesis. We reject the idea that our treatment does nothing, which means we accept the idea that our treatment does something, and we conclude that the games program does, in fact, change the self-esteem of these students compared to the general population. So in this case, rather than going back to the drawing board, rather than going back to theories about self-esteem and trying to come up with a new program, in this case we would say, you know what, this program works for the population of students, so I'm going to publish this work, I'm going to call up other schools, I'm going to tell them, look, if you're looking for a way to increase the self-esteem of your students, what happened to my sample indicates that this program will work for a population of students, i.e. it'll work for the students at your school. All right, so that was look number 2. Any questions about that? Is it starting to kind of seep in, make sense? All right, we're going to take one more look, all right, just to kind of let this multiply its effects. And in reality, it's the exact same situation. We're going to see that it's the exact same situation again, the exact same procedure, but now with a completely different example. So we saw 2 looks at the same kind of hypothetical situation. Let's take a look at another hypothetical situation. So this is Harlow's monkeys. We're going to take a look at Harlow's studies on infant attachment. And we're going to see that when Harlow was trying to make his decision on the preferences of monkeys, will they prefer food or will they prefer comfort, he used the exact same testing procedures that we're using and introducing right now. So just in case you're unfamiliar with the experiment, I'll give you a brief little bit of a background. The video is embedded in the PowerPoint files if you want to see the entire video later on, or just in case this doesn't work in the next 10, 9, 8, 7, 6, 5, 4, 3, 2, all right. So this is the Harlow infant attachment experiment. And what they did was they raised infants in captivity. And these infants were isolated, and they were given a surrogate mother. And this surrogate mother had both, is that as far as my internet's going to get me today? All right, so this surrogate mother was made of terry cloth. So she was very comfortable. She kind of felt like a plush, cuddly, probably like teddy bear. And it also had a bottle from which the monkey could feed. All right, there we go. The terry cloth mother with the bottle. So this is what the infant was used to. This is what the infant was exposed to. And then in the experiment, they had two mothers, and what they did was they separated comfort and food. They took the terry cloth, and the one mother just had the terry cloth, without any food in it. The other mother had a wire mesh body, but it had the bottle of food. And what they did was they measured which one will the infant choose. Will it choose the comfort or will it choose the food? And if you've been exposed to this, it looks like the internet is not cooperating, not my friend. But if you've been exposed to this before, you will know that what eventually they found was that infant monkeys will choose comfort over food. So they actually spent way more time with the terry cloth mother than they did with the mother that provided sustenance. And this kind of revolutionized the ideas of parenting. This is why parents, before this became known, if they provided their children with food, clothing, and shelter, they were killing it as parents, because that's what you need. You need to provide the basic necessities. Nowadays, they understand that there's more to being a parent. There's the emotional aspect of it as well, and a lot of that came about because of Harlow's research on these monkeys. So Harlow would have measured how long did they spend with the terry cloth mother, and then he would have needed to have analyzed that information to determine if they spend a different amount of time with the terry cloth mother than they do with the wire mesh mother. So there's an image of the two mothers right there. That's what the wire mesh one looked like. That's what the terry cloth one looked like. So let's take a look one more time how this hypothesis testing procedure we've been working on would be applied to this real life situation. So in the classic study of infant attachment, Harlow placed infant monkeys in cages with two artificial surrogate mothers. One mother was made from bare wire mesh and contained a baby bottle from which the infants could feed. The other mother was made from soft terry cloth and did not provide any access to food. Harlow observed the infant monkeys and recorded how much time per day was spent with each mother. In a typical day, the infant spent a total of 18 hours clinging to one of the two mothers. If there was no preference between the two, you would expect the time to be divided evenly with an average of 9 hours for each of the mothers and a standard deviation of 5.29. So that's stretching what we know a little bit just for the purposes of education. We would not know those means and standard deviations, but that's just a little bit of a simplification so we can introduce this idea. However, the typical monkey spent around 15 hours per day with the terry cloth mother, indicating a strong preference for the soft, cuddly mother. Suppose a sample of 9 infant monkeys averaged 15.3 hours per day with the terry cloth mother. Is the result sufficient to conclude that the monkey spent significantly more time with the softer mother than would be expected if there was no preference? Is this result big enough to say that the population of monkeys prefers the terry cloth mother? We're going to use a two-tailed test with an alpha of 0.05. So there's that alpha of 0.05 one more time. Same procedure, same 5 steps we're going to go through. So step number 1, restate the question as a research hypothesis and a null hypothesis about the population. So we're asking, is there a preference for the terry cloth mother or for the wire mesh mother? And the research hypothesis is that there is a preference for one of the mothers. And we write this by saying that the mean time spent with the terry cloth mother does not equal the mean time spent with the wire mesh mother. And because we know that they spend 18 hours per day with one of these two mothers, right? Between the two mothers, they spend 18 hours a day clinging to both of those. If there was a preference for one, we can write that as the mean for the terry cloth mother does not equal 9 hours. So in the population of individuals, we'll draw the population over here because I don't want to confuse it. In the population of monkeys that don't prefer either mother, the mean for that population is going to be 9 hours, right? On average, monkeys are going to like to spend 9 hours with the terry cloth mother and 9 hours with the wire mesh mother. That's exactly the population we would expect if there's no preference. Now in this population, you're going to have some monkeys over here that love that wire mesh mother, right? So these are all the wire mesh monkey loving monkeys here. And then these ones over here are the ones that are the terry cloth loving monkeys, right? So they're the ones that are extreme in terms of how much time they spend with the terry cloth. These are the ones that are extreme in terms of how much time they spend with the wire mesh. But on average, that population spends 9 hours with the terry cloth mother, 9 hours with the wire mesh mother. If this is what monkeys really are like, then there's no preference between the wire mesh and the terry cloth mother. Does that make sense, that logic? All right. So that's the research hypothesis. The research hypothesis is that monkeys do not come from this population. There's a preference for one of the mothers. So they do not belong to this no preference population. That's the research hypothesis. The mean does not equal 9 hours. The null hypothesis is that there is no preference for either mother. That means that the mean time spent with the terry cloth mother is equal to the mean time spent with the wire mesh mother. If they're spending 18 hours between the two mothers, the only way that happens is if they're spending 9 hours with each, i.e. they belong to this 9-hour population. So sure, you're going to have some that prefer the wire mesh, you're going to have some that prefer the terry cloth, but on average, there's no preference between the two mothers in the population of monkeys in the world. So where do our monkeys come from? Do they come from this no preference population? Or do they belong to a different treated population? That's what we're going to be asking. All right, so that's our null and our research hypothesis. Next step, determine the characteristics of the comparison distribution. We'll see how to do this the next chapter. For right now, I want you to get it very solid, very straight. This is the population. Population of individuals. Unfair to compare your sample mean to a distribution of individuals. Unfair. So what we need to do is we need to change it into a distribution of sample means. That's step 2. We have to change it into this distribution of sample means, and we're going to see how to do that next chapter, but for right now it's got to be given to you. And in this case, the mean of our distribution of sample means is still 9 hours. And the standard deviation of our distribution of sample means is 1.76. All right, and we'll see how to do that again next chapter. Importantly, not the same as this one who has a standard deviation, I think it was 5.29. Okay, not the same distributions. We have to compare our sample of monkeys to a distribution of samples. All right, step 3, set a cutoff sample score or critical value. This is the target against which you're going to compare the results of your study. This has to be on the unit normal distribution curve for no other reason than we don't have an appendix of this curve here. So we transform it into z-scores so that we can use that table, and we find the line in the sand, and lo and behold, same line we found before. So these lines in the sand are based on your alpha level. So our alpha level hasn't changed. Lines in the sand, they don't change either. All right, step 4, determine your sample score on the cutoff distribution. So we know in our comparison distribution, let's get rid of that mean there because we don't know where it is yet. So we know, we've measured the monkeys that we have in our sample. We've measured those 9 monkeys. And their mean score was 15.3 hours. Whoops, 15.3 hours. So on this distribution of sample means, if that's 9 hours, 15.3 is somewhere over here. Right? It's got to be somewhere over there. But we don't know how far. Specifically, we don't know if it's crossed any lines, because we don't have any lines here. So what we need to do is we need to transform that, like we did before, into a z-score. Well, there's your sample mean. That's your raw score. There's the mean of your distribution. There's the standard deviation of your distribution. There's the z-score formula we've been using since chapter 2. You plug it all in, and your z-score for your sample is 3.57. 3.57 on your unit normal distribution, if that's a mean of 0, that's positive 1.96. 3.57 has crossed that line. Your monkeys are over here. So, what does this mean? Well, spoiler alert, we crossed the line. It means that our treatment has an effect. Another way to think about that is that either our monkeys belong to a different population. They do not belong to this population that likes terry cloth mother and wire mesh mother the same. They do not belong to this population where on average they spend 9 hours with each mother. They've crossed the line. They probably belong to another population. So they either belong to another population or we just ended up with 9 of the most terry cloth loving monkeys out there. So that's highly unlikely that we ended up with that many terry cloth loving monkeys. So it's much more likely that they never belonged to this population in the first place. They belong to another population. Monkeys actually belong to a population where they love the terry cloth mother more. So that's the spoiler. How do we get to that conclusion? Well, we take a look at this slide. If the sample z-score is beyond the cutoff z-score, there's your sample z-score. Yes, it is beyond. Yes, it did cross that line. So what do? We accept the research hypothesis and we reject the null hypothesis. So we reject the idea that their love for each mother is the same. We accept the idea that it's different. If, on the other hand, we ended up somewhere here in the body, we would accept the null hypothesis and we reject the research hypothesis. We would say that their monkeys in the population have no preference between the two mothers. So we are clearly rejecting the null hypothesis. Our monkeys clearly have crossed into that tail end. And we can conclude that monkeys actually do prefer the terry cloth mother. Monkeys actually do prefer comfort over sustenance. They do have emotional needs that need to be met that are more important than biological needs. And again, this is exactly the same procedure that Harlow and Zimmermann would have used to analyze their data to come to the conclusions that basically change the face of parent-infant attachment and infant and child development theories. All right, that was the third look. That was a lot, but I did want to make sure that we got like 3 separate looks at this hypothesis testing procedure just to let it all kind of sink in. Any final questions on this logic, this idea? All right, so just as a brief wrap up, in terms of your homework assignment, nothing yet. All right, we're letting this sink in. This is a crucial part of the course here. So I would highly recommend, if this seemed a little fast for you today, if you're still kind of sitting there going, what exactly happened? Go to the YouTube videos, follow along in those. You can pause those, you can slow it down if you need to. You can go back and rewatch things. But there's no homework due yet. We need one last little piece, which is finding these cutoff scores before you have the full package that you need. So just kind of let this permeate through your mind. Get used to it. Take another look at it on the videos. I highly recommend it. Look over this concept a few times. Let it sink in. And then also, do not forget that now that we're in this hypothesis testing portion of the course, your pre-tests are going to get more challenging. They are still highly valuable. So please make sure that you attempt the pre-test. Give it the old college try, as they say. But don't be alarmed if you're not understanding exactly what's going on. Don't be alarmed if you can't figure out all of the questions on the pretest. Take comfort in the fact that the program is set up with the MyStatLab study plan where you can earn all your mastery points and get 100% on your pretests. All right, so that is what I wanted to cover for today. So we got 5 minutes left. If you want to call it an early day, feel free. If you have any quick questions, I will be happy to come by and help you out. But other than that, we are done for today.